go. Now it's unmuted. Okay, welcome back, everybody. We are in week 10, so we're going to wrap things up. Like I had mentioned on Friday's class, the topics for this material aren't going to show up on homework. They're not going to show up on the final, but they are going to be exceptionally useful as you go through the rest of your classes because ordinary differential equations show up all over the place inside of engineering. In particular, if you are a chemical engineering student, this is going to show up a lot in 113, as well as 120. I always get 20 and 22 confused, but the controls class, it shows up a lot over there as well. If you're not a chemical engineer, you're still going to use them, I promise. They're covered in much more detail in Math 20D. If you're a UCSD student, you'll probably take Math 20D as part of whatever your degree is. The reason that I chose to cover these, even though there is a class for them and not linear algebra, for which there is also a class for them, is because these come up more often. It's much more likely that you would have to solve a differential equation than a massive set of linear equations, hence why we're doing it. Also, the syntax, once we set up the equation, I think when you see it, you'll see that it's very similar to what fsolve and f0 look like in terms of setting up the structure of the problem. But it has actually a couple of advantages. Mainly, you don't have to guess anything. You don't have to plot anything. You just say, here's the problem I want to solve, and it solves it. There's no iteration to it or anything like that. So homework 5 is due today. 6 will get posted a little bit after lecture today. 6 is about anonymous functions, so it should be a little bit shorter than the rest of them, and it'll be due the last day of class, which is Friday. And then on Friday, the final project will get posted, and I'll talk about that a little bit more either on Wednesday or Friday. But today and Wednesday, we're going to talk about differential equations, and then that'll pretty much wrap up the class for us. I haven't decided exactly what I want to do on Friday. We'll see. I will figure it out. But let's switch over to Excel and take a few notes. This will take probably the first half of the class or maybe a little bit more. I want you to know what we're doing and why, so that I don't just throw a bunch of math at you and you have no idea where anything is coming from. So a reasonable place to start is what's an ODE? I keep saying ordinary differential equation or ODE. That is what ODE stands for. It stands for ordinary differential equation. And that is in contrast to a different type, which is called a PDE, which is a partial differential equation. PDEs are generally much more challenging to solve. You probably can't do it analytically, like with pen and paper. And even to solve them on a computer is substantially more challenging than an ODE. So we won't, basically, is the idea. MATLAB can solve them. It has several solvers that can do PDEs. But we're not going to get into PDEs. Typically, they look something like this. So how do you know if you're seeing an ODE or not? And you may have already seen them previously. The two variables I'm going to use are x and y. So it would look something like dy dx is equal to some kind of a function of x and y. And then coming along with it is usually something else that looks along the lines of y when it's evaluated at x is equal to 0, is equal to typically some number, but also they just call it y0. So this term, this is your differential, which is not interpreted any differently than it is in your calculus classes. I don't think there's a technical name for this, but I usually call it the ODE function. The entire term over here, both of those lumped together, that's your full ODE. This term over here can be split in different ways, but this is usually called your initial condition. And it's called the initial condition even if it doesn't have anything to do with time. So the word initial kind of implies time, but it doesn't have to be a variable of time. The variable on top of the differential, so in this case y, this is your dependent variable. And the one on the bottom, the x, let me see if I can draw that inside of there, just the x. This is your independent variable. So that's what an ODE looks like when you encounter it, right? If you see something that looks like that, written somewhere on a piece of paper somewhere or in a class or something like that, you have now seen an ODE. I don't know where that may have come up yet in your curriculum, because everybody's kind of at different places in their curriculum when they're in this class. But if you haven't seen it, you will, and if you have, that should look familiar. One key point to keep in mind is that when you see the dy and the dx, those aren't products of d and x or d and y. They're kind of lumped together. So those are not separate variables. The d is what we call an operator. Or more specifically, it's not actually just one. Usually we think of it as just one, but it's actually something like d dx is an operator. So an operator is something that implies performing some kind of an operation. It's like square root, right? You don't think of, when you see a square root, you don't think it's like a product of something that looks like a v and whatever's underneath there. It's saying do some kind of an operation to the number that's underneath the square root. So when you see dy and dx, those should never be broken apart. It's never a d times a y or a d times an x. Where do they come from? How do we end up with something like this? It depends on what class you're in. Sometimes they're defined. So from your physics courses, whether you've had to write them in ODE form yet or not, we've actually seen in this class that the rate of change of position with respect to time is defined as velocity. If you dig around in enough physics books, you can probably find somebody that tries to derive that, but for the most part, we just define it and say the rate of change with respect to time for any of the positions is called velocity. And similarly, if you then take the resulting derivative of velocity with respect to time, this is typically just flat out defined as acceleration. I don't know that you could find, quote unquote, a derivation for that. Typically, it's just defined. Other times they come from conservation equations. And this part requires two pieces. One is to recall a definition from calculus. Probably, you wouldn't have gotten to it, I think, in pre-calc, but I'm guessing like one of the very first days in Calc 1, you would have learned the definition of a derivative, which would look something like dy dx is equal to the limit as a little bit of x, let's say delta x, goes to 0, and then this weird looking expression of y evaluated at x plus delta x minus y evaluated at x, all of that divided by delta x. And it might have been h's. That's another very common one, like y evaluated at x plus h, and then divided by h and letting h go to 0. They're all equivalent. At least for our purposes, they're going to be equivalent. So this usually gets combined, or this, I should say, it gets combined. This arises naturally from conservation equations. Most conservation equations are written as accumulation. Accumulation is equal to in minus out plus generation minus consumption. And the majority of your engineering classes are based on one or another conservation equations, mass or momentum, or there's linear momentum, angular momentum, energy, all that kind of stuff. And we can write these kinds of conservation equations even on quantities that are not strictly speaking conserved. So mass is certainly conserved. You can't create it or destroy it. But you could write this on a molecular species, right? And we can break molecules and destroy those and create those. And this still holds because we've got those generation and consumption terms. So as an example, if you had a cylindrical reactor, how could you get an ordinary differential equation out of this? Well, the types of derivations that we do or have done, depending on where you are in your particular curriculum, is to start off with something that feels at least somewhat more natural, in the sense that we can draw a cylinder. And we can send stuff into the cylinder and get stuff out of the cylinder over on this side. And then we just sort of start marking this up almost in a way that feels overly obvious. So at the inlet, it has at some volume V. We don't know what the volume V is over here. And then as it goes through the tube has a volume of delta V. So that by the time you get out the other side over here, this is now V plus delta V. So we don't think of length, we think of volume here. And you can send in some moles of A over here, and you get out some moles of A over here. And what we typically do, this is a type of a balance called a shell balance, is just say, I don't know what Na is over here, but I know that it's the value of Na evaluated at V, and this is the value of Na evaluated at V plus delta V. It's just, quote unquote, a little bit different. We don't really care what the difference is, it's just different. If there's a reaction that occurs inside of here, then the rate of reaction within this little volume is Ra times delta V. So this is typically how we would start to write these, and then we could write conservation of mass. And you'll get this in 100 and 102 and 113, 101A, 101B, 101C. They all start life like this. We say accumulation is equal to in minus out plus generation minus consumption. If it's operating at steady state, usually this is 0 because things don't change in time if it's at steady state. And so we end up with an expression that looks like 0, and now we add up all the things going in. So that's Na evaluated at V minus whatever's going out, which is Na evaluated at V plus delta V. And the entire generation and consumption term here, that's your reaction term. So this looks like Ra times delta V. And that just gets all lumped together as Ra delta V. And now we play games until we can get back to that definition from calculus. So if we rearrange a little bit, and if we divide by delta V, then we'll get Na at V plus delta V minus Na of V is equal to Ra. If we divided both sides by delta V, then the delta V that's next to Ra would go away, and we would get a delta V over here. And now you can see that's really close to that definition that we had from calculus, which is here. It looks like some value evaluated at a little bit more minus where it was a moment ago, divided by the amount of change that we have. That's exactly what we've got down here, and it just sort of arises naturally from balancing things as they go into and out of various volumes. And so now we would take the limit as delta V goes to 0. Once you do that, that entire term over here on the left, well, not just that, all of it, including the limit, this is now our derivative. So we would say dNA dV is equal to Ra. And then we would have to specify some kind of an initial condition. For example, Na when V is initially 0, right, before it enters the reactor, is probably some kind of initial condition, and we would just call it Na0. So this is an example of the other way that we often generate an ordinary differential equation, is to just look at some physical phenomenon over a very small area, typically a volume element, but it could be a length element or something like that. Let's do one more really quick. I won't go into quite as much detail on this one. Conservation of energy. In your fluid mechanics class, which actually, whether you're a chemical engineer or a nano engineer, you end up looking at something like this. If you had something like a pipe, and maybe it goes up a little bit, it comes over here and then narrows. So we'll try and draw that pipe as best we can. Let's say that there's fluid coming in over here and there's fluid coming out over here. If this thing is particularly well insulated, so I'm going to try to draw insulation as best I can on here. We tackle this sort of a problem with conservation of energy. So there's some energy going into a volume over here and there's some energy coming out over here. It started off at V is equal to V, whatever that means, and then it ended up at V plus delta V. Right, it went some direction through there. Our conservation would say this is equal to energy at V minus energy at V plus delta V. If you do that whole trick all over again, you end up seeing that the change in energy is 0. Right, you rearrange stuff, divide by delta V, and let delta V go to 0. You end up with another differential equation. Usually we play some more games with this. So if you want to see where like 100 and 102 might come in, we would say energy is typically equal to like an internal energy plus some kinetic energy plus some potential energy. And so if we substitute that in instead of dE, dV, now you get an expression that should look or will look familiar from thermo. A change with respect to volume of something like U plus KE plus PE is equal to 0. And from that, we can get things like the Bernoulli equation or any number of the energy balances that we try to use inside of 100 and 102 often pop out from something like this. Yeah?
So is U potential energy or?
Yeah, in this case it is. It's an internal energy.
Oh, so like thermal energy.
That's what U is, yeah.
Oh, okay, okay.
Mm-hmm.
All right, okay.
I was just wondering, inside the initial condition, it said X is equal to something. I'm not really sure what it was. It was in the beginning of the notes, just saying that there's an initial condition.
This one?
Is that equal to 0?
Yeah, that should say X is equal to 0.
Okay.
It doesn't necessarily have to be equal to 0. It could be anywhere. All it means is that we know the value of Y at some particular value of X. It's exceedingly rare that we don't know it, or that we know it anywhere other than 0. That we just tend to know stuff at 0 from the way that we set up problems.
Thank you.
So from this one, if you were so inclined, you could spread out that derivative and take the derivative of each one of these individual ones. And I'm not going to write this any further than here, because where you choose to go from here kind of depends on what you're trying to accomplish. So each of these represents a separate change, and you can add them all up like this. And depending on your particular problem, some of those may go to 0, some of them may stick around. It just sort of depends. But at any rate, they're all coming from some kind of a conservation equation or definition. That's pretty much the only two places where we can grab a differential equation. So that's what you can expect in your future classes. How do you solve an ODE? I should say too, as far as the setup goes, we're going to treat that just like we would the equations that we were using for F0 and Fsolve, in the sense that I'm not expecting you to be able to set any of those up. That's what is generated naturally from the other classes. So we're going to assume that we have the equation. There are two different ways that you can solve these things. Option one is to do what's called an analytical solution. This is equivalent to solving it by hand. And at least at UCSD, this is Math 20D. So 20D teaches you some of the ways that we can solve these things by hand. And I'm going to use a word here that I don't like to use too often, but it's only relative to other things. The easiest class of ODEs to solve are called separable ODEs. And I say that they are easiest, but I did not say that they are easy. Of the ODEs that you can solve, those are the easiest ones, but even those can be very challenging to solve. The main idea of separable ODEs is to group the relevant variables on opposite sides of the equation and then integrate. So that's why I say they're the easiest ones, because they don't require a solution that's really new. They require a minor amount of algebra, and then for you to remember all those rules from like Calc 1, 2, and 3 about how do I integrate all kinds of different expressions. But in that sense, they haven't changed anything from the other ones. So for example, suppose the reaction rate from that reactor example that we had up a moment ago is RA is equal to minus K times NA. What if we wanted to solve the ODE that we had before? Well, that ODE started off life as dNA dV is equal to RA. So we substitute in for RA and get minus KNA. And now we do that main idea, which is group relevant variables on opposite sides. So we've got an NA here. We're going to take this NA and shove it over to the left-hand side. There's no V's over here, but we do have a dV over here, so we're going to take that and push it to the other side. And the result is dNA over NA is equal to minus K times dV. This is now separated, so you can imagine integrating both sides of these. And here, these integrals can very rapidly become kind of ugly looking. But at least in principle, these are sort of quote-unquote standard calculus steps, right? Whatever's left here is just integrated as though it's a single variable. But that doesn't mean that it's easy, right? There are plenty of integrals that just become too difficult to solve. What you would be left with is natural log of NA is equal to minus K times V plus a constant. The evaluation of that constant comes from the initial condition. So the initial condition sets C. Usually we don't see it as plus C. It is always possible to write it as plus C, but typically we don't see it as plus C. It works its way out a little bit differently. Since we're not solving any of these by hand in here, I'm not going to sort of go over that math. The general idea is you put them in as the bounds of the equations here, and that just changes the way that it looks after you integrate it. But if, for example, the initial condition is that NA evaluated at V is equal to 0 is some term, and let's call it NA0, that value of C would be a number, right? It would be somehow proportional to NA0. And you could rearrange that after a little bit of algebra, and you would end up with NA is equal to NA0 times the exponential of minus KV. The reason that I went to the effort to actually solve one of these by hand is because this, not so much this particular answer, but this thing that we got after we solved it is important to point out. The thing that we got is not a number. The solution is a function. So unlike F0 and Fsolve, we shouldn't expect a number to pop out after we solve a differential equation. We should expect something that is somehow related to this function. What MATLAB provides is, I guess I can type this here and then we'll just draw it. MATLAB is going to provide a vector of v and a vector of NA. It's not going to provide the function itself. On the other hand, though, a plot of MATLAB's output should line up essentially perfectly, indistinguishably, from the analytic solution. And it's really good at doing those. We're going to see a little bit of that towards the end of class today. But it's really important to keep in mind the thing that we're getting is not a number. Oftentimes we are interested in the value of whatever that variable is, say NA, at the end of the domain that we're interested in. But nevertheless, you can't get to the end of the domain until you've integrated all the way through the rest of the domain so that you know what's coming out the other side. So it's not that they all look like a number times an exponential of something raised to a negative value, but they will all be a function. When they are solved, they are all functions. Usually that's too difficult to do by hand. So the other option for a numeric or for a solution to an ODE is a numerical solution, i.e. with a computer. Most algorithms are going to approximate the derivative as a difference. As a difference. And we've done this actually on a homework previously. We had something like dy dx was approximated as a little bit of change in y over a little bit of change in x. I think this was on homework 3. We did a numerical integration like this. The same approach can work with an ordinary differential equation, although they're usually structured slightly differently because an ODE is asking for slightly different things than just a straight numerical integration. But the big difference is this approximation is actually pretty poor, the one that we've used. It's not bad when delta x is really tiny and y behaves fairly well, but most algorithms that you use for numerical integration will be way more accurate than this difference equation, but they will all be based on difference equations. So when we're using MATLAB, we'll use a function called ODE45 to improve on this approximation. The 4.5 that you see in that function, ODE45, is pronounced that way. It's 4.5, not 45. And the reason for that is because it refers to, you may have heard of a series of different, it's two people, Runge-Kutta, but a bunch of algorithms that are somehow related to Runge-Kutta, and this is an RK45 algorithm that sits underneath there, which sounds fancy, but it's talking about the precision of the algorithm. There are some others that we're not going to worry about right now. There's an ODE23, there's an ODE15S. If you do that fun command, help fun, you'll see a bunch of other ones. Help fun for more, but it's rare that you're going to need any more than just 4.5. 4.5 covers the vast majority of stuff. The solution always follows the same setup. And this is sort of the part that I want you to take away from our general discussion of ODE45, or of ODEs being solved with MATLAB in general. What's the solution step that I have to follow? The generation of the ODEs, yeah, I gave you some ideas of that over the last like 20 minutes, but those are generally going to come from your other classes. Once you have them and you need to solve them, particularly in MATLAB, what do I do? The first step is something like the root finding form that we had before, in the sense that you have to move the derivative, for example, the dy dx term, onto the left, and everything else on the right. So in that sense, it is an algebraic operation. It's exceedingly rare that you will ever have a derivative that is like squared or, you know, inside of a square root. It's never going to be like inside of a sine or something like that. So that process, just like the root finding form process, is usually like one step of algebra, if that. They're kind of naturally written on the left anyway, so you may not have to move them at all. You have to identify the initial condition. Usually it'll be given, but you need to make a note of it because you're going to need it. And then you have to identify the range over which you want to solve the ODE. So this is usually your starting point and your stopping point, and it's also usually given. So that all sits in a similar place, at least logically, in the development of the code, as rearranging things to root finding form does, and well, I should say the other way around, finding the equation and the unknown in root finding form and then rearranging it to root finding form is more or less what you're doing here. You're just identifying bits and pieces of the problem and rearranging it in a way that plays well with MATLAB. Then you actually start the coding process, which is to create a local function for the ODE. Then you pass whatever you came up with in 2, 3, and 4 to the ODE 4, 5 function, and then you plot it. So 4, 5, and 6 are kind of the equivalent of creating your root finding function as a local function and then passing it to F0 or Fsolve and then checking the result somehow, right? It follows a similar pattern here. There are a couple of elements that are related here. So the initial condition here usually correlates to the starting point. So whenever you see the initial condition written, for example, the way that we had it written up above, that was that NA evaluated at V is equal to 0 is equal to NA 0. Typically, we would call this part over here, like if we were coding it, we would restrict ourselves and say this is the initial condition. That whole statement is really the initial condition, but when you're coding it, we typically just think about the right-hand side as the initial condition, but the start refers to this. So the initial condition occurs at the beginning value of V. You wouldn't say the initial condition starts at Z, or at V is equal to 0, and then start your integration at like 6 or something like that, right? You would start your integration at 0. So what we're going to do is switch over to MATLAB, and we're going to solve that expression that we just saw a moment ago, which is dNA dV is minus kNA. The initial condition, we'll actually pick some values here. So NA of V is equal to 0. We'll set that equal to some number like 2.3. So that's what we want to do. We want to solve that. And then we want to plot over the range from V is equal to 0 to V is equal to 4. That's sort of a bare bones setup of a problem statement in order to solve a differential equation. It gives you the differential, it gives you the initial condition, and it gives you the range. So the elements that we have on here, that's your range. This is your initial condition, and this is your ODE. And you have to have all of those parts before you can use MATLAB, and it's not always easy to figure them out. And then we're going to compare that plot to the exact answer, which is NA is NA0, which we just derived a moment ago, e to the minus kV. those two ought to line up virtually indistinguishably. There should be almost no difference between the two. In much the same way that if we were to apply like the quadratic equation or something, the result that we get from solving that analytically ought to line up perfectly with something like F0 or Fsolve. There should be basically no difference between the two. And since that function happens to look like a nice, simple looking function, we will practice our anonymous functions in order to create that plot. So I'll just wait a moment in case anybody is writing anything down, but we're going to switch over to MATLAB here in a second. So I'm just going to leave myself a note here that we're solving dNA dV is minus KNA. The initial condition is NA at V is equal to 0 is 2.3 from 0 to 4. But let's compare it first to the exact solution. So K, oh, did we define K? I don't think I defined K previously. K is 0.9. I'm just going to say that's given, even though it wasn't given. It should have been given. I just overlooked it. You couldn't solve it if you didn't know the value of K. We know that the exact form for NA is a function of V, and specifically, it's NA0 times the exponential of minus K times V. So if we're going to try to use an anonymous function like that, we've also got to know that NA0 is 2.3, which is also given. So this NA was our exact solution, or our analytic solution. And then we can plot this with fplot. We only need to go from 0 to 4 because that was the range that we were given. And especially with differential equations, you should always, I mean, you should be doing it all of the time. But label your axes. That's a perfect example of why an anonymous function is kind of helpful. It's easy to set up with something like this. So there's our exact solution. NA, it's in that example that we had, is mole of A. And A appears to be undergoing a chemical reaction, so it's getting consumed. And by the time it leaves the reactor at V is equal to 4, there's not much left. There's essentially 0 of the stuff left. There's a little bit left, but not very much. So everything that we did right there was just looking at the analytic solution. To produce the numeric solution with ODE 4.5, we think back of the 4-step, well, it was really 6 steps, but only 3 of them are particularly important for what we want. We already have the derivative on one side, it's dNA dV. We already know the initial condition and the range, so we can go right to step 4, which was to create the local function. That local function is, I would say, once again, not easy, but probably easier than the F0 stuff because it reads almost identical to the way that it's written. So you can write dNA dV is equal to whatever you want it to be called. Just don't call it RFF because it's not that MATLAB would have a problem with that. It's just, it's not a root finding thing. So I'm just going to call it my ODE. And then no matter what the actual function is, you always give it the 2 variables. So you always give it V and NA, and they always go in that pattern. So if you think back to the first thing that I did when I set up and sort of identified the ODE, V here is your independent variable, and NA is your dependent variable. It always goes in that particular pattern. And then the thing that you put inside of the function is whatever the differential is. So for example, minus K times NA. So these, with very little rearrangement, typically look exactly like whatever you've got written down on paper somewhere, which makes them, I would say, slightly easier to debug than the root finding functions. Again, not to say that they are easy, just in comparison to the other ones, I would say they might be a little bit easier. And then we need a k, so we can throw a k as 0.9 in there. And then how do we pass that to ODE 45? Well, the same way that we might start out writing F0, blah, 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 we start off writing ODE 45, blah, 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 blah. The autofill will pop up, and it'll say, okay, the first thing you got to do is tell me the function. That looks just like we did for fsolve and F0. So we say the variables we're interested in are V and NA, and the function is my ODE of V and NA. What's the span? MATLAB thinks of everything, at least in default terms, in terms of time, but it doesn't need to be time. It can be anything that you want. This is just asking what's the range over which you would like this to be solved, and that's 0 to 4. And then the last one is the initial conditions. So whatever you want the initial condition to be, which in this case is NA0. It's important to keep in mind that this is not a guess. NA0 is not a guess like it was for F0 or for fsolve. We know the value of the function at that particular point in the independent variables range. It's not a guess. There is no guessing involved in ODE 45. Everyone will come up with the same answer regardless, because there's no option for guessing in here. The outputs that ODE 45 are going to provide, again, aren't a single value, and it's not exactly a function. It's MATLAB, or it's ODE 45's interpretation of a function, which is a list of values of V and a list of values of NA. So this will look like V and NA over here. I'm going to rename those as, instead of V and NA, we've already got an NA up here, and it was the function. And just to sort of distinguish them, there's a lot of V's and NA's floating around. These are the solutions. So I'm going to call them VSOL and NASOL. Just as a reminder to us that those are not the same thing as the variables, but there's no reason you couldn't call them V and NA. It would just be a little confusing because you've already got some of those floating around. VSOL and NASOL are vectors. Specifically, they're column vectors. But they're always going to be of unknown length. There are ways to set the length of those ahead of time so that you know how many elements they're going to be. But ODE 45 is going to pick enough elements of V so that it gets a pretty good answer. But we don't know how many that is ahead of time, and usually we don't care. We just let it do its thing. It's usually on the order of like 50 to 100 elements, but it's kind of arbitrary. It can be a lot of different numbers. So if we want to add that, we can say, hold on, and then just plot these regularly. This is not an F plot because these are coming out as vectors. And then we should add a legend to distinguish between the exact answer, which is the first one that we did, and the approximate answer, which is the one that ODE 45 is going to give. In your local function, MATLAB will nearly always complain that the input argument V might be unused. Ignore it. ODE 45 requires it to be there, even if it's not used in the actual function. So ignore that requirement. Just leave it there. So if we run this script, we should get the two pretty much exactly on top of each other. Which, as far as I'm concerned, those two are pretty much on top of each other. If you wanted to view it a little bit more, you could add another plot on there of exactly the same thing, but throw some red X's on there. And you will see that they are, it's indistinguishable, right? That was the word that I had used previously. There's no way to tell the difference between the exact solution and the approximate solution, certainly not by just looking at it. If I just like zoom in on one of these things, I'm not going to be able to see any difference at all between those 2 points. So I can zoom in here and then zoom in again, and I can just go as close as I want to this, and they will always be right on top of each other, right? I'm out to whatever, 4 decimal points or something like that. Everything is just lined up right on top of each other, as accurately as the plot can show at any rate. That's sort of the level of reliability that we have to assume is present even if we can't get the analytic solution. Because for a lot of problems, there is no analytic solution. It's not possible to get any kind of closed form solution to a lot of different differential equations. It's not doable. It's not that it's hard. It's not that, oh, maybe grad students can do it or PhDs can do it. There's just no solution, and you have to solve them numerically. But that's not a bad thing, right? It's like solving an implicit equation, like we saw the x is equal to cosine of x. We can just solve it to whatever degree of precision we need, and that usually stops around a few decimal points. We're in the same boat here with ODE 4.5, or just generally any of the ODE solvers. They are approximate, but they're a really good approximation. And for engineering purposes, plenty good. There's nothing wrong with that. So we're going to wrap it up there. We'll come back on Wednesday, solve a couple more of these, and then see how the syntax expands for solving systems of differential equations, which again is not, I won't say it's easy, but I would say that it is easier than when we went from F0 to Fsolve, because there's no guessing in this one. You just change the structure and it solves them just as efficiently as it would with 1, as with 50 or 10 or whatever. You don't have to change nearly anything about the solution procedure on here. It just looks of a slightly different shape for the data. So I'll wrap it up there. If you're watching on Twitch, I'm still over in Canvas chat, so if you have any questions after the lecture, I'll be over there for a few minutes. Otherwise, I'll see you back here on Wednesday. Bye, y'all.